Okay, so our next speaker this morning is Dr. Grace Metcalfe from the Air Force Office of Scientific Research. Grace is the program manager for both the Quantum Information Science portfolio and for the Atomic and Molecular Physics portfolio, and she also leads the physical science team within AFOSR. Prior to joining AFOSR, Grace was previously a program manager at the Army Research Laboratory. Over her career, Dr. Metcalfe conducted multifaceted research in atomic physics, precision measurements, microcavity resonators, ultrafast spectroscopy, terahertz radiation, metamaterials, all areas that positioned her well for her involvement in the quantum information revolution. So we are pleased to welcome her today to describe the portfolio of quantum activities at AFOSR. Grace, take it away.
Dave, thank you for the very kind introduction and invitation to speak at the 3rd Annual Chicago Quantum Summit. It's really a pleasure to be here today, particularly with all the exciting quantum information science technology activities that we've been hearing about the last day or so that are centered around the Illinois region, as well as across the nation and the globe. As you know, as many of you know, AFOSR is a funding agency. We are responsible for the discovery, shaping, and championing of basic research for all of the Air Force and now the Space Force as well. Some have asked me before, what exactly is basic research? The DoD defines basic research as the systematic study directed toward greater knowledge or understanding of the fundamental aspects of phenomena and of observable facts without specific applications towards processes or products in mind. I'd like to highlight the last underlined portion, without specific applications towards processes or products in mind. The way I think about basic research is that there are no specific applications, more because there is such a vast potential to impact a multitude of applications, precisely because the science explored here is so fundamental. This is what is so powerful about basic research. AFOSR supports basic research in a variety of ways through traditional grants, including single investigator awards within the US as well as internationally, historically Black colleges and universities, minority serving institutions, and early career grants, such as the AFOSR Young Investigator Program and the PCASE, or Presidential Early Career Award for Scientists and Engineers. We also support larger collaborative efforts, including Centers of Excellence, the OSD MIRI, or Multidisciplinary University Research Initiative Program, and the OSD Laboratory University Collaboration Initiative and the OSD Defense Enterprise Science Initiative, otherwise known as the Lucy and DESI programs. AFOSR also funds the basic research executed at the Air Force Research Lab, or AFRL. This is a topic of great interest to the community and has been brought up several times during the summit. I will also emphasize that AFOSR supports numerous workforce development programs, including for undergraduate students. One example is through the Assure program in collaboration with NSF and the AFRL Scholars Program. Graduate students through the National Defense Science and Engineering Graduate, or NDSEG Fellowship Program, as well as the AFRL Scholars Program, and postdoctoral fellows through the AFRL Science and Technology Fellowship. There are some links at the end of my charts if you wish to find out more about these various opportunities. As I give this presentation, you may be wondering why the U.S. Air Force invests in basic research at all. I've asked myself the same question, and the answer really goes back to World Wars I and II. Those conflicts made it perilously clear the impact of decades of neglect of aeronautical-related R&D. During World War I, U.S. pilots, for the most part, flew second-hand European planes, even though the first successful airplane was invented in the U.S. by the Wright brothers. Note the collaboration here between the US and international partners. During World War II, the head of the Air Force, General Arnold, who also happened to have been taught to fly by the Wright brothers, recognized that the first essential of air power is preeminence in research. So in 1944, he convened the first group of top US scientists and engineers to provide independent advice to the Air Force on science and technical matters. The Scientific Advisory Board continues to this day. Of course, it wasn't just the Air Force that understood the importance of science during the wars. Dr. Vannevar Bush famously articulated the significance of science for national security in Science, the Endless Frontier, a report to President Roosevelt in July of 1945. So, shortly after the end of World War II, in October of 1951, AFOSR was created in recognition of the critical role of basic research for the Air Force. The original building you see in the picture here was located in downtown Baltimore, Maryland, but it no longer stands. Today, AFOSR is situated in Arlington, Virginia. Though the original AFOSR building may not have lasted, the AFOSR mission from 1951 still persists today, almost 70 years later. And that mission is to discover, shape, and champion basic research that profoundly impacts the future Air Force, and now the Space Force as well. One of the easiest ways to demonstrate the influence of basic research is by looking at the history of Nobel Prize-winning research. Since its establishment in 1951, AFOSR has sponsored 82 primary researchers who went on to become Nobel laureates in physics, chemistry, physiology, medicine, and economics. On average, these laureates received AFOSR funding 17 years prior to winning their Nobel awards. One of the early Nobel laureates supported by AFOSR that you've most likely heard of was Dr. Charles Townes. AFOSR sponsored in 1953, as part of the Joint Services Electronics Program, Dr. Townes and his colleagues for their basic research that led to the first maser, or microwave amplification by stimulated emission of radiation. As is well known, the maser precipitated the development of the laser and an explosion of laser-related breakthroughs, many of which were also AFOSR supported, including atomic clocks. Dr. Townes and his team's work eventually led to a Nobel Prize in Physics about a decade later. Another Nobel laureate well known to this community is Dr. Stephen Chu. AFOSR began supporting Dr. Chu in 1988, shortly after he joined Stanford University from Bell Labs, for research into the laser cooling and trapping of atoms, which eventually led to a 1,000-fold increase in atomic clock accuracy. In 1997, Dr. Chu was awarded the Nobel Prize in Physics, shared with Drs. Cohen-Tanuji and Phillips. Then another well-known AFOSR-supported Nobel laureate to this community is Dr. David Wineland, whom AFOSR began supporting in 1982. Dr. Wineland demonstrated the first quantum logic gate with 2 quantum bits and won the 2012 Nobel Prize in Physics for his groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. So this leads to the reason why we're here today, quantum information science. So why does the Department of Defense care about quantum information science? One understandable motivation is that we have seen the usefulness of quantum science, especially in the role of atomic clocks and GPS for navigation. There's a recent report by the Defense Science Board that gives a fairly nice description of several applications of quantum technologies that are of interest to the Department of Defense. It states at the core, the promise and impacts of quantum science and technology are about the collection, generation, processing, and communication of information. The report illustrates 3 technology areas with critical value, which are probably not surprising to you. These are quantum sensing for timing and positioning, magnetometry, and gravimeters as examples. Quantum computing, for example, for cryptography, signal processing, simulation, and entanglement distribution for teleportation and distributed computing, amongst other potential applications. One of the challenges, but also what makes quantum information so powerful, is that it is inherently multidisciplinary. We've heard this several times already during the summit. Quantum mechanics was originally the merging of exciting new physics concepts of the time with the elegant formalism of mathematics. Quantum mechanics or quantum physics merged with information science to give us quantum information science. But as the field progressed, it became clear that other disciplines play important roles, such as photonics, computer science, material science, engineering, chemistry, and more. It's exciting to see how many collaborative efforts, such as these new national quantum centers, bring together the expertise from so many of these different communities. Within AFOSR, the multidisciplinary aspect of quantum information science is long recognized by the multiple AFOSR portfolios that contribute to the field. This includes not only the quantum information science program that I manage, but also programs in information assurance and cybersecurity, materials with extreme properties, atomic and molecular physics, optoelectronics and photonics, condensed matter physics, molecular dynamics, and theoretical chemistry. And last but not least, our international offices around the world that focuses on engagements with partnerships with the broader international community. AFOSR is open to and encourages foreign collaborations. Another example of the multidisciplinary aspect of quantum information science can be seen here in the progression of quantum information science over several decades through the OSD MURI program. Now, the intent of the MURI program is to bring together ideas, not from multiple universities, but from multiple disciplines, to solve problems that cannot be solved otherwise. This dense chart is not meant for you to strain your eyes and read, but see in a snapshot how the MURI efforts have grown and evolved over the years with the different categories of quantum computing in black, quantum networking in orange, timing in green, and quantum sensing in blue. In the next chart, I will pull out some examples. So what can be learned by examining the MURI programs in quantum information science? Firstly, as also mentioned by the previous speaker, you can see from the span of several decades that it takes long-term sustained research and development to advance the field. I will give two examples, the first one being quantum simulation. There were other important research efforts leading up to this, but in the early 2000s, a seminal experiment was performed that demonstrated how an ensemble of cold atoms trapped in an optical lattice could be used to simulate strongly correlated materials. Soon after, AFOSR, ARO, and DARPA got together, engaged with the research community, and began developing coordinated programs in quantum simulation. The result was the joint launch of the fiscal year 2007 AFOSR MURI on quantum simulations of condensed matter systems using ultra-cold atomic gases and the DARPA Optical Lattice Emulator, or OLE program. Near the end of those programs, lessons learned helped to formulate the next stage of programs, namely two fiscal year 2013 MURIs, the Army Research Office, or ARO MURI, on non-equilibrium many-body dynamics, and the AFOSR MURI on new quantum phases of matter. These really were aimed at exploring what other novel phenomena could be simulated with exquisitely controlled cold atoms. Several successful advancements made during the MURI and DARPA OLE programs are now leveraged in other programs, including the current DARPA program on optimization with NISQ devices. The second example I will discuss is in the area of optoelectronics for sensing and transduction. While there are several smaller efforts over the years, The first large program on optomechanics was launched by DARPA around 2010 on optical radiation cooling and heating in integrated devices, or ORCID. This was primarily focused on cavity optomechanics for non-cryogenic sensing at the standard quantum limit. A year later, DARPA launched the Quantum Assisted Sensing and Readout, or QUASAR program, to develop atom or atom-like sensors, including hybrid and entangled quantum sensors that operate near or below the standard quantum limit. As the quantum transduction efforts were coming to an end in the DARPA QUASAR program, AFOSR, ARO, and the Laboratory for Physical Sciences, or LPS, worked together to develop a multi-team MIRI program to expand the development of controllable optomechanical devices towards new quantum transduction mechanisms between disparate quantum systems. Soon after, ONR launched a MIRI on quantum optomechanics to further exploit the intrinsically quantum behavior of nanomechanical systems, including for new or improved quantum logic operations and precision measurements relevant to sensing. As the MIRI on quantum transduction was coming to a close, LPS and ARO engaged with the research community and other agencies to create the Cross-Quantum Technology Systems, or COTS program, which continues to push the frontiers of quantum state transfer from microwave to optical wavelengths. I'm delighted to see continued support in these areas in the new national quantum centers. I hope my examples here demonstrated the importance of exchanging ideas and working together between different agencies and between different researchers for larger, more impactful efforts. I hope my illustrations also show how creative ideas, often supported by smaller core programs like single investigator awards, can seed larger programs that continuously evolve, sometimes non-linearly, into new and unexpected areas. Additionally, close engagements with the academic community and industry plays a significant role for funding agencies in shaping focused and valuable programs. Personally, I see many exciting opportunities ahead through collaborative efforts between different communities. This includes exploring new quantum resources and enhanced quantum control, developing quantum programming languages and novel quantum algorithms, bridging the gap between theory and experiment, smart design of quantum materials, development of quantum components with unique requirements for quantum information science and technology, and the discovery of new useful applications for quantum information science and technology. I was delighted to see several of these areas discussed in the center talks yesterday. So what will be required to get us from the basic research of ingenious ideas to practical applications? Well, we can hope. It's unlikely it will be a simple leap across this valley. It's more likely a long, steady climb requiring sustained, long-term R&D. One cannot predict when innovation will occur. And for quantum information science and technology, there's not always an intuitive classical analogy. The path also requires a holistic approach. If you look closely, successful climbers are often not alone. As mentioned several times during the summit, partnerships between government, academia, and industry are critical, both nationally and internationally. I also echo the statement regarding the importance of workforce. Here, I would encourage the community to think beyond the standard STEM pipeline model. In regards to applications, this will require casting a wide net, as mentioned before, as well as developing a common language to translate some of the more complex and non-intuitive ideas of quantum physics. I was happy to hear about the communications positions mentioned by one of the centers yesterday in this regard. Finally, as I was preparing this presentation, I came across a statement in the AFOSR 60th monograph that nicely sums up why I do what I do at AFOSR. It says, "The great thing about basic research is the mystery of it. It essentially takes you in directions that you may never have expected or imagined. And I look very much forward to seeing where this quantum information science and technology community takes the field. Thank you for your attention. And I will leave you with a page of several links if you would like to know more about AFOSR and our various opportunities. Thank you again, and I'm happy to take any questions.
Okay, thank you, Grace, very much for that really interesting outline of the history of AFOSR. I did not know a lot of that, and the ongoing research in quantum information. We do have a few minutes for questions, so people can type those in the chat room. There are some coming in. I think all the PIs are always interested in funding, but we have a lot of students online and they're interested in jobs. So a lot of the questions are regarding what job opportunities are there in the Air Force for quantum engineers. What kind of experience do they need? How can they get involved?
I would say that there are opportunities if you want to do research in the lab, there are several research facilities within the Air Force that are located in Rome, New York, in Albuquerque, New Mexico, in Dayton, Ohio, for example. And there are job openings for every level, from student interns to postdocs to full-time researchers doing their own projects within the Air Force lab.
So there's also some other questions coming in. This is an interesting question, I thought. What do you see emerging in the context of technology development on the isomorphism between, question just went away on my screen, between black hole physics and condensed matter physics?
That's an interesting question. I think that we are finding out more and more unexpected similarities than we have before. And even between black hole physics, for example, or high energy physics and quantum information science. So I have a colleague who has a MIRI program actually on quantum holography, and this is working in collaboration with DOE as well. I think that there are a lot of overlaps that we may not have seen before, and it's really much more apparent when we bring people from different communities together.
Yeah, I think we're seeing a lot of cross-cutting disciplines like this going on. So some of the other questions, I think, again, have to do with how to break into the field. I think that's of importance to people. I guess I would like to hear a little bit more about how you plan to interface with the 3 NSF centers and the DOE and the 5 DOE centers. This is sort of a new thing in our field, and I think everybody's going to try to figure out how that interfaces with the traditional ways in which funding has come through the agencies like yours.
So I think the engagements are various levels. It could be between program manager to program manager, which we already work pretty well together. It can be between, the program managers and the researchers, which I think there's a lot of integration and overlap, complementary programs between the different agencies, and the researchers are well known to the program managers from different agencies, the DOE, NSF, DOD, including the Army, and the Navy, as well as the Air Force. I think there's also another level of engagement between the researchers at the Air Force and other DOD agencies and the researchers at the centers. And so I think there's plenty of opportunities to really pull together and really make this an impactful effort.
Okay, so there's also a number of questions coming in on quantum communications. You mentioned that in your last slide, and there was a lot of discussion of that yesterday, some of the centers being involved in that. So I think the questions have to do with what is the AFOSR's role in that, and how do you plan to get involved in things like the quantum internet and programs such as that?
Oh, is this Sorry, I mistook is this about communicating quantum information science, or this is about
This is about quantum communications as in quantum internet, I think, more, or
okay.
things like
that. So our focus is looking at the underlying foundations, really looking at distributed entanglement. So, and that really goes and impacts a variety of areas, which includes computing, looking at, say, distributed quantum computing, or it could impact, say, sensing, looking at a network of distributed sensors, or even timing. So we are looking at distributed entanglement, and as we are a basic research funding agency, looking at really the foundational aspects of it, the underlying principles, and how we can, for example, understand how one would distribute entanglements across multiple quantum entities. What is the best configuration? What is the best way to generate the entanglement? How would you measure it? How would you verify what you think you have? How would you characterize it? And how the different configurations lend itself to different types of applications.
And a specific question in this regard, which I have no idea the answer of, is the Space Force exploring quantum communication in space?
Oh, is the Space Force? Was that the question?
Yeah,
so we are working Yes, we are working very closely with the Space Force. The basic research element of the Space Force it resides within AFOSR. So looking at what is essential for creating advantages in space using quantum information science is a high priority for us.
So I have a question, I guess, that's on my mind, which is you've talked a lot about, of course, AFOSR, since that's where you are, but how coordinated are the other defense agencies in this endeavor?
I would say that there has been really the coordination. It has there's been a tight coordination over several decades. As you know, some of the examples I gave were really joint programs that were created by the different agencies coming together to focus on certain topics. And this has been something that has been ongoing for longer than I've been at the DoD, much longer. And I don't foresee this changing.
So maybe one more question, and this is an interesting one. I mentioned I was intrigued earlier that people are logging in on this from all over the world, which I think is impressive. And so someone made a question that in Nigeria, most of the study in quantum information is more theoretical in nature due to the nature of the economy there. And the question is, how can developing nations get involved in quantum information, applying QI knowledge? I wonder if you have any thoughts on that. This is kind of a broad question, I guess.
I think the key is really collaborations and partnerships. So if your institution lends itself more to theoretical investigations, it's a perfect opportunity to partner with other organizations, other countries, other institutions that, say, would have the resources for experimental demonstrations of the theory that you are proposing or investigating. And there's a variety of ways that we can help facilitate this. We have people on the ground in various countries that are really looking to increase the engagement. So that's definitely one area we can do it. But the Air Force researchers engage with the international community regularly. The AFRL enterprise has just opened a new open innovation center in Rome, New York, that is right outside the gates of the facility. So international partners are welcome to come and do a sabbatical, for example, if they wish, to work on quantum information science and other types of research at this new center. It's called the Innovare Center.
Okay, very interesting. Okay, so we're out of time. Grace, thank you very much. That was very intriguing, and thank you very much for your presentation.
Thank you.